space, we're going to use one dimension is going to be encoded 0, and the other dimension, and another dimension is going to be encoded 1. And the idea is that these dimensions are going to be separated from each other, and so that local operations on 1 or 2 of these 5 or 7 qubits is not going to be able to mix up encoded 0 with encoded 1. And in particular, it has the following property. When you have it, this is a rigorous definition. A distance d quantum error correcting code means that if somebody looks at a subset of why do I say this? Isn't it d minus 1? Why did I say d minus 1 or 2? I think it's d minus 1. Yeah, so a distance d error correcting code, quantum error correcting code means that if your adversary or if the environment or if anybody looks at any set of d minus 1 or fewer qubits, they learn nothing about the encoded state. So how can you say that formally? Yeah. So what I mean is you take an arbitrary logical state. So you take an arbitrary logical state. It's like psi logical is equal to alpha 0 logical plus beta 1 logical. Then you get rho logical is equal to psi a 7 qubit density or 5 qubit density matrix, whatever. And I'm saying if you trace out all but like d minus 1 qubits, so you're left with the reduced density matrix on d minus 1 qubits, you should end up with a density matrix that's independent of alpha and beta. And this is an interesting property. It's different from a classical error correcting code, right? So a classical error correcting code, like 0 goes to 0, 0, 0, and 1 goes to 1, 1, 1. If you just look at one of these qubits, you learn everything, right? If you look at the first qubit, that tells you what, or if you look at the first bit, that tells you what the logical bit is. So quantum error correcting codes are not going to be able to do that. Like a distance 3 quantum error correcting code, you can look at any 2 of the qubits, and you just see the maximally mixed 2 qubit density matrix. You learn absolutely nothing about the state. Okay. All right, so that's, I'll give lots of examples. That's sort of the rough idea. The other interesting idea, which was first observed, I guess, by Peter Shor, was that errors actually are digital. So you can imagine that quantum error correction is impossible because quantum errors, unlike classical, so classical errors have to be continuous. They can flip a 0 to a 1, or they can collapse a 1 to a 0, but there's nothing else they can do. Whereas a quantum error, you can take ket 0 and rotate it to like square root of 1 minus epsilon ket 0 plus square root of epsilon 1. So tiny rotation is possible, and there's a whole continuous parameterization there. So how can you hope to correct these tiny continuous errors? But nonetheless, you can. And the reason essentially is just because these poly errors form a basis. Sorry, yeah, the poly operators, the 1 qubit poly operators form a basis. The 2 qubit poly operators form a basis for the 2 qubit. So any, let's see, what's the statement? So any 2 by 2 matrix can be written as a complex combination of these 4 poly matrices. So the set of 2 by 2 matrices, it's 4-dimensional, 4 complex numbers, and 4 complex. That's why 4 matrices. And the same is true in higher dimensions. So if you have k qubits, the k qubit poly operators, so there's 4 to the k of them, those form a basis for the set of all 2 to the k by 2 to the k matrices.
Hermitian.
No, I don't need Hermitian. So over the complex numbers, these form a basis for all matrices. Over the real numbers, they form a basis for the Hermitian matrices. Right, and what this means is that any error, even a continuous error, even a channel, not a unitary, whatever, it can be expanded as a combination of these basic poly matrices. And so if you have, and so what that means intuitively is if you have an error correction procedure that works against poly errors, then it works automatically against arbitrary errors, because arbitrary errors can be expanded out on the basis of poly errors. This is sort of what it looks like. So here, I mean, this is a very crude illustration of it. So psi is my encoded state. Then we have some recovery procedure that works on poly errors, and so